There's a mysterious zone far out in our solar system. It's a region of ice worlds, some solitary, some with moons. Their names may be unfamiliar: Eris, Makemake, Haumea, but they hold clues to all our origins. And the first of these worlds, and the one we'll reach in 2015, is the king of the Kuiper Belt, Pluto. The long journey of NASA's New Horizons mission began in 2006 aboard America's biggest, baddest rocket, tricked out with every conceivable booster.
We built a very light spacecraft and bought a very large launch vehicle, and the combination is ferocious.
But in some sense, it all began in 1930 with Clyde Tombaugh, 24 years old and fresh off a farm in Kansas, but willing to spend long hours scanning star fields to find a moving point of light. Humanity's first glimpse of Pluto. The dream of actually getting to Pluto began with a 6-year-old boy in love with science, who grew up to lead a team of brilliant researchers and engineers with dogged persistence through decades of planning and building and testing. A race against time just to get to the launch pad.
Exploring the outer solar system, because it's so far, takes a lot of time. It requires a lot of patience, a lot of dedication, a lot of perseverance, but it's the frontier.
Assuming all goes well at Pluto, NASA may choose to extend the adventure further out into the Kuiper Belt, the solar system's mysterious third zone.
This is maybe the one chance in my lifetime that we're going to get a spacecraft out there and look up close at one of these Kuiper Belt objects.
December 6, 2014.
We have an long wake up of the New Horizons spacecraft.
New Horizons wakes up for the last time from hibernation.
New Horizons is speeding towards Pluto at a phenomenal rate, and we can't wait for it to get there.
January 27, 2015, 6 months of approach science begins. July 14, 2015, New Horizons' long journey, 3 billion miles, 9 years in flight, and 85 years of speculation about Pluto climaxes in one day of close approach and flyby.
You know, we're rounding third base and we're headed home.
The dream, the adventure, the promise of discovery. That's what makes 2015 the year of Pluto. Studying Pluto and its neighbors from Earth is one of the toughest challenges in astronomy. It takes the largest telescopes and most advanced instrumentation on the planet. And it's tough even for the Hubble Space Telescope. And it takes time, from the discovery of Pluto in 1930 to NASA approving the New Horizons mission in 2001 to arriving at the planet in 2015. It's been 85 years, and time passing is definitely an actor in our story. But it's the combination of human skill, cutting-edge image processing, and sheer bloody-minded persistence that has resulted in the most important discoveries. And that's a tale as true today as back in 1930, when Pluto was first found by Clyde Tombaugh. In 2011, at the SETI Institute near San Francisco, Mark Showalter used Hubble data to discover 2 new moons around Pluto, although he was actually looking for possible rings. Showalter has found rings associated with small moons around other planets.
And that was kind of the motivation for checking out Pluto. It's got 2 little satellites. Satellites raise clouds of dust. Let's see what might be there.
It's easy to take artistic license to show what Pluto's rings might look like. In reality, it's incredibly hard to see faint objects against the dense background star field and the glare from Pluto and its large moon, Charon.
We came up with this trick where you take the images and then you rotate the camera 90 degrees, you take more images, and if you do that all just right, you can do this thing where all that glare cancels out, and what we're left with is just the rings. We can think of it as a stack of images. Think of it as like a cube looking down. So let's turn it on its side. So now if we start peeling off the layers and looking downward through the stack, things suddenly become much, much cleaner. For example, Hydra and Nix show up very, very cleanly. But the thing that immediately caught my eye was this little dot. right there. It's not a perfectly sharp hot pixel like over here, and that's what made it pretty convincing to me that we had seen a very small moon of Pluto that nobody had seen before.
To be sure you've detected a real moon or planet, you have to show it's moving, unlike the background stars.
The thing that makes moons distinctive is if we come back later, they'd all have shifted because they all orbit the central planet. This required a great deal of patience to then wait about 6 days until we got our next set of observations of the Pluto system. Sure enough, the object was still there. It had moved by just about the right amount to be something orbiting Pluto, and we knew we had a moon.
Next year, Showalter and colleagues went back and built on lessons learned to see what else might be there. Summer 2012. Now, Mark had 15 more days of Hubble observations.
Now, what you can see here are 3 time steps. Each of those time steps is actually about 45 minutes of data. That means it's long enough that the little moons move. It's moving back and forth in this 3-frame sequence. Hydra is moving, Nix is moving. I mean, it doesn't take a rocket scientist to say that that looks like a little moon of Pluto. It's moving just the way the others are. They're all going around the planet in the same direction. And so it was just a couple of weeks later that we made the announcement that the 5th moon had been discovered.
Patience, persistence, ingenuity. That was exactly what led to the discovery of Pluto back in 1930. In Kansas in the 1920s, Clyde Tombaugh grew up in hard times and built telescopes using leftover farm implements. To check the accuracy of his best telescope, he sent drawings of Mars and Jupiter to the Lowell Observatory in Flagstaff, Arizona. They were looking for staff, and he was hired. Along with observing the stars, he stoked the furnace and shoveled snow. But one assignment made history. Day after day, he'd use this machine, known as a blink comparator, to look for anything in his images that moved. It was tedious, painstaking work, but on plates taken on January 23rd and 29th and analyzed in February, he saw a small dot that did move against the fixed stars. Announcing the results after careful confirmation, the observatory made it easy to find the new planet by adding arrows.
This is an incredible work of observational astronomy, and having done something similar but with much more powerful tools, I can really appreciate his achievement.
For decades, Pluto remained, more or less, a point of light. But in the mid-70s, Dale Cruikshank and colleagues attached cameras with infrared filters to a telescope at Kitt Peak.
Detectors or sensors had been improved, and larger telescopes had become available. Well, we did that work in 1976 and found evidence for frozen methane on Pluto's surface. It was several years later that we found evidence for the other ices.
In 1978, astronomers Jim Christie and Bob Harrington analyzed new plates taken at the U.S. Naval Observatory in Flagstaff. Christie noted an elongation to the north of Pluto. 1 month later, the bump had disappeared. From this and other evidence, they concluded that Pluto, like Earth, had a moon, Charon. From eclipses between Pluto and Charon occurring in the 1980s, astronomers calculated that the moon was almost half the size of its parent body, so large that both objects spin around their mutual center of gravity, outside Pluto. Pluto and Charon were the first double dwarf planet combo discovered in our solar system. Using the basic physics of their orbits and the distance between them, astronomers could calculate their mass and size. Pluto was a little smaller than Earth's moon, about 1,500 miles in diameter, and had only 1/10 its mass. Between 1985 and 1990, astronomers were in luck. As Pluto and Charon orbited their mutual center of gravity, each passed in turn in front of the other. The so-called mutual events allowed astronomers like Mark Bowie to capture the changing patterns of light. Patiently, Bowie created a map of Pluto. Pluto turned out to have one of the 2 most contrasty surfaces in the entire solar system. In the mid-90s, Bowie and Alan Stern used the Hubble Space Telescope to make the first direct images of Pluto's surface.
And it's exciting to Mark and I and to our whole scientific team to be able to see this object that no humans really could glimpse as a real planet, as a real object
in the solar system previously.
In 2005, Hal Weaver and Alan Stern used the Hubble for another close-up look at Pluto and Charon. They discovered two small, dim moons where only Charon had been seen before. Now we know from Mark Showalter's work that there are two more moons, making the current total of 5, and that Pluto is a genuine mini-planetary system. From its size and orbit, astronomers estimated that Pluto is perhaps 70% rock and 30% ice. That makes it one of the largest of a whole new class of objects, the ice dwarf planets, making up what's known as the Kuiper Belt. This region is named for Gerhard Kuiper, a leading mid-20th century planetary astronomer. Kuiper suggested that the solar system didn't end with Neptune and Pluto, but that there should be a disk of other worlds beyond them. In 1992, from a mountaintop in Hawaii, David Jewett and Jane Liu found the first Kuiper Belt object. They were using new and highly sensitive CCDs, like the sensors in a modern digital camera. But their technique was essentially an updated version of Tombaugh's work. Take carefully registered images of a patch of sky and see if anything moves against the distant stars. This one, QB1, did just that. It was only a few hundred kilometers across, 10 times smaller than Pluto, but still huge compared to a comet. Since then, teams of astronomers have found around 2,000 KBOs. Informed by cutting-edge astronomy, but with a fair dose of artistic license, let's take a trip through this third zone of our solar system.
We used to think of the solar system consisting of two different types of planets. The planets we call the terrestrial planets, which are Earth-like planets. That would be Mercury, Venus, Earth, and Mars.
Next out, the asteroid belt. Fragments of worlds smashed to pieces by gravitation and collisions. Then come the 4 gas giants. Jupiter and its moons. Saturn with its magnificent rings. Uranus, also ringed. And Neptune.
And then Pluto was this kind of, odd guy out. It was this little object at the edge of the solar system. And then when we found all these other Kuiper Belt objects, this is kind of almost a third type of object.
So for the first time ever, we'll be able to fly by a brand new object, an object that's been forming for billions of years, and understand what outer parts of the solar system are all about.
By July 2015, we'll know for sure what Pluto and its moons look like, and that will provide breakthrough information on all those other ice dwarf planets, the most numerous planetary objects in the entire solar system that make up the Kuiper Belt. Actually, the Kuiper Belt is more like a donut, bulging up above and down below the ecliptic where most of the planets move.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
Let's now visit 5 named KBOs in the exact positions they'll be in on July 14th, 2015, the day when New Horizons flies by Pluto. Quaoa was one of the first Kuiper Belt objects discovered. It's about 1,000 kilometers in diameter, a reddish world, covered in water ice, methane, and ethane. And like many KBOs, it has a tiny moon of its own, Wayuat. Up above and down below the plane of the solar system, numerous KBOs have been flung about by Neptune's gravity. This region is known as the scattered disk. One of the largest of these KBOs, Eris, is close in size to Pluto and is made of rock and methane ice. Astronomers categorize KBOs by the tilt of their orbits relative to the plane of the solar system. And one of the more highly inclined orbits belongs to Makemake, named for a Hawaiian creation deity.
Some of these have methane or water ice on their surfaces. Some of them just seem to be covered in some brownish gunk. There are gray objects out there. There are brown objects out there. There seem to be distinct populations.
Some of them seem to be very spherical, and so they probably have warm interiors, and then others are peculiar shapes which suggest they're very cold and strong.
Perhaps the most bizarre and unexpected KBO is Haumea, a KBO shaped like an American football, made of rock and ice. It's white with red splotches, and orbited by at least 2 moons. One of the strangest orbits of any KBO belongs to Sedna, discovered in 2003. Its orbit is the most eccentric of any KBO now known, bringing it as close as 76 AU to the Sun, but then carrying it outward to 936 times the Earth-Sun distance. Sedna's strange 11,000-year orbit seems to link it to an even vaster cloud of objects, ready for exploration by future generations. The Oort cloud is an immense icebox of long-period comets, from 10 to 100 times more distant than the Kuiper Belt, surrounding all the known worlds of our solar system.
There's a real record of the early history of the solar system out there in cold storage at the edge of the solar system.
This is what was left over. Pluto is the first member of that group.
But to begin humanity's exploration of the Kuiper Belt, you first have to get to Pluto. And that means getting a mission approved, a spacecraft designed and built, and delivered to the launch pad on time. And none of that was easy. "2015 may be the year of Pluto, but getting there has taken many long years of effort. And for New Horizons, there's a date when things got started: 1989. It was the year when George Herbert Walker Bush became president and the Berlin Wall fell. Far from Earth, it was also the year when NASA's Voyager spacecraft flew by Neptune and returned the first images of its moon, Triton. Hairstyles of some New Horizons scientists were very different, but for them, May 5th, 1989 was a most important date.
That's the day that I marched into the then Division Director for Planetary Science at NASA headquarters, Jeff Briggs, as a graduate student, and asked him why we aren't studying a mission to Pluto. And he responded, "Because no one's ever asked me before. That seems like a brilliant idea. Why don't we do that?"
Space missions rely on hundreds, if not thousands of people, but sometimes it takes someone with passion and persistence to make things happen. And for New Horizons, that's Alan Stern.
I was interested in this when I was a boy, so I've been somewhere between in the groove and stuck in a rut for 40 years.
There'd been some thought about sending one of the twin Voyager spacecraft past Pluto to complete the exploration of the known solar system. But in the 70s, the scientific establishment wasn't convinced Pluto was all that interesting. Young grad students like Alan, Mark Bowie, and Fran Bagenal thought differently.
Back in, about late 1989 or so, there was a bunch of us who were really keen to go to Pluto.
And the thing that drew me to it the most was the fact that we knew so little. Here's the frontier.
So it was a bit of an opportunity for young people to come in and say, hey, where are we going to go next? What's the next great frontier that we should go explore? And it was clear, out to the Kuiper Belt.
Alan, Fran, Mark, and a small band of enthusiasts became known as the Pluto Underground.
So we realized to make this happen, we had to get together and campaign hard to make the case to go there and explore this little planet with all its moons.
All through the 90s, there were many competing plans for a Pluto mission, like the Pluto Fast Flyby, the Pluto Kuiper Express. A Pluto mission was on, then off, then on, then off.
If the Pluto mission had been a cat, it would have been dead long ago because they only get 9 lives. And we've had significantly more than 9 stoppages and odd twists and turns.
What finally turned the tide was the National Academy's Decadal Survey, a consensus document from leading planetary scientists that ranked a Kuiper Belt Pluto mission highest in priority for medium-class budgets. Finally, after competitive proposals were evaluated, New Horizons, which teamed Alan Stern with the Johns Hopkins Applied Physics Laboratory, APL, and several other institutions across the country, was selected by NASA on November 29, 2001. Now, plans on paper became metal in clean rooms. In 2004, lead scientist Alan Stern described the mission's key science objective.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
The very best resolution of current telescopes looking at Pluto would give this kind of fuzzy image of a much more familiar world. But here's what New Horizons would see if flying over New York City, lakes in Central Park, wharves on the Hudson River.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this first mission to Pluto, the questions are basic. What do Pluto and Charon look like? What are they made of? How do their atmospheres behave?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
The long-range imager, LORRI, will be used for navigation approaching Pluto and close-up views during the flyby. The wide-angle camera, RALPH, has both visible light and infrared sensors to map Pluto and Charon and characterize their icy surfaces. There are two fields and particles detectors to probe the solar wind at Pluto. The large radio antenna is an essential communications device, but both REX and ALICE, an ultraviolet imaging spectrometer, are part of experiments to analyze Pluto's atmosphere. And there's the Venetia Burney Student Dust Counter, built by undergrads at UC Boulder, and honoring the schoolgirl who named Pluto back in 1930. Together, the 7 science instruments comprise the most powerful set of detectors ever sent on a first flyby of any world in our solar system. But their innovative and highly miniaturized design means that even when all are operating, they draw less power than half a 60-watt bulb, and they're intended to work together seamlessly. After building comes testing, but always with an eye on the clock and the calendar.
It's very, very important that we launch in either 2006 or 2007. We have to make that deadline.
If you want to fly to Pluto on the quickest route, you need Jupiter in position. And that means we have to launch in January of 2006.
It feels a little bit like being strapped to a train going 500 miles an hour.
The test program involves teams of engineers at Johns Hopkins APL and then at NASA's Goddard Space Flight Center.
Once we launch this, we can't go after with a screwdriver. We can't go fix anything that isn't working.
We make sure that we carry plenty of spare equipment on board the spacecraft. If our main computer breaks, we have a backup. If our main transmitter breaks, we have a backup.
One of the things we do is we put the whole spacecraft on a gigantic vibration table, a paint shaker, and shake it. And then test it after that, and shake it again and test it again. So that's what we're doing from now until launch.
Along with testing the spacecraft, New Horizons needs to train and test its human operators. And for a mission planned to reach Pluto in 2015, it's important to have young people on board early, so they'll be around at close approach.
It's good that we can do that, so they will have both the time, the focus to stay with the mission over this long period of time.
Many of the faces you see around Mission Control in 2004 and 2005 are young and enthusiastic spacecraft engineers.
Normally we're focused on subsystems and instruments in the spacecraft surviving that duration, but for people we have to have a longevity plan.
They'd be committing the prime of their careers to this mission to Pluto, knowing they'd be a decade older when New Horizons reaches its primary target.
The ability to practice things in those years far out there are all part of the planning now to assure mission success then.
How old are you going to be?
In 2015? I don't know, somewhere in my 40s.
Oh, and you're a youngster.
Yes.
In late 2005, the action shifts to Cape Canaveral. New Horizons may be light and relatively small, but launching it to Pluto requires America's most powerful rocket, the Atlas V. New Horizons will be traveling so far from the sun that solar panels wouldn't be sufficient. So the Department of Energy delivered an RTG that would power the Pluto mission by turning heat from the radioactive decay of plutonium into electricity. Working round the clock, they arrive at Pad 41 before dawn. On behalf of NASA and the entire New Horizons team, Stern wanted to be the last to bid the spacecraft bon voyage before closing up the hatch. On January 19, 2006, after 17 years of planning, building, and testing, a picture-perfect launch that thrilled onlookers in Florida and the mission operations team back at Johns Hopkins in Maryland.
We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
Despite immense technical and timetable challenges, the mission had made its window and was on its way. New Horizons' velocity at launch was the fastest ever, traveling almost 60 times faster than a jetliner. In just 9 hours, it passed the orbit of the Moon. Apollo had taken almost 10 times that long. 1 year later, a slingshot gravity assist from the giant planet Jupiter provided another 2 kilometers per second boost, cutting travel time to Pluto by 3 full years. But this was more than just a jump in speed. The Jupiter flyby was a scientific dress rehearsal for Pluto. New Horizons instruments returned detailed images of Jupiter's clouds, moons, and rings.
We got the night shine. Oh, wow, look at that.
Then it was off across the empty ocean of space, with no new land in sight till Pluto in 2015. The spacecraft had been tested and passed with flying colors. Now it was time to test the humans and the ground systems. July 5th, 2013, it's day 1 of a 9-day encounter rehearsal.
The main success criteria for this rehearsal is for the spacecraft to flawlessly perform its activities as if it were at Pluto, with everything the same, except that Pluto's not there.
The dates in 2013 were carefully chosen so that Earth-received times would be identical to those for the real encounter in 2015. Mission managers wanted scientists and engineers to experience the stress of time-critical 24/7 operations expected for July 2015.
We're flying by an object that is a huge distance from Earth, and we're trying to hit a box that's 100 by 150 kilometers wide. And that then leads into maneuver planning and trajectory control needed to thread that needle and hit that small box. It's way the heck out there.
This rehearsal would actually be uploading commands to New Horizons to instruct the spacecraft to run through the exact same set of observations as in 2015.
There definitely is an element of risk involved, but from one standpoint, if you didn't do any simulation with the real spacecraft at all, you could argue that could pose more risk because you don't want such a critical activity only being done once on flight.
Those are all invaluable to get us ready and practiced for the one and only shot we'll have to explore the Pluto system.
We've been waiting 12 years since we wrote the proposals to do this rehearsal. It's the last big step before we can do the encounter.
We think that we are about 10 million miles out from Pluto and closing.
But so far, so good. We're off to the races. Today is our 2,724th day in flight. This has been a long time coming, literally. I only want to say thanks for all the work. Let them eat cake.
July 12th, 2013, standing in for July 14th, 2015. This is it, a minute-by-minute simulation of Encounter Day. It's make or break.
Well, it's the most important because we've best been spending the 24 hours of the most intense activities that we've been running on the spacecraft, and this is the longest that we've been out of contact since we've entered encounter rehearsal.
This may be a rehearsal, but New Horizons has been firing its thrusters and spinning in space, identical maneuvers to those planned for 2015. On Encounter Day, the spacecraft will be too busy taking data to send back images. That's why its first simple "I'm alive" message will be so important.
Sometime within the next minute, DSS 43 should lock up on the signal.
We're good. We're nominal. Spacecraft's nominal, and it looks like all the observations that we had planned between the last track and this track
happened.
So this gives us good confidence that at least the spacecraft has been performing all of those twists and turns that we've been anticipating it to over the last 7 days.
I like to say that at the flyby, I don't want to be learning anything about the ground system or the spacecraft or the team. I want to be learning only about the Pluto system.
No spacecraft has ever been to Pluto, nor will ever go back in our lifetime.
Pluto is every child's favorite planet. You know, you ask anyone under the age of 6, and they're going to say Pluto.
We don't exactly know what Pluto looks like, but it looks very exciting from the images we have from the Hubble Space Telescope so far. We really can't wait to get there and see what it actually looks like. So if anybody says that Pluto is boring or not important, no way.
Before New Horizons arrives at Pluto, most everything we think we know about the planet and its moons is up for grabs.
Virtually every place we've sent a spacecraft on a first reconnaissance mission like this, that we find out that our Earth-based notions were flat wrong. So I'll tell you what we expect, but before anything, what we expect is to be surprised.
From the 1990s through today, Stern has been consistent in avoiding speculation.
You get the same answer everybody's gotten from me for almost 20 years. I don't make predictions, except for one. My best guess is we're going to find something wonderful.
But in the final months leading up to the July 2015 encounter, it's hard for most humans not to imagine what we'll see. Many planetary scientists, like Paul Schenk, base their expectations on what we saw when Voyager 2 reached Neptune, and specifically as it flew by its moon, Triton.
Voyager was a 10-year-long exploration of the outer solar system, and every time they got to a planet, it was basically the first time anybody had really seen those bodies. So when they got to Jupiter, they were greeted with enormous surprises. The erupting volcanoes on Io were just completely unexpected. And so when they got to Uranus, there were more surprises. The exotic trains of Miranda and Ariel, for example, were not expected. So by the time they got to Neptune, they were kind of accustomed to the idea that they were going to be surprised. And sure enough, Triton completely blew them away.
Bonnie Barati was at NASA's Jet Propulsion Lab as the first images of Triton, a moon of nearly 1,700 miles diameter, came down.
Triton was almost a twin of Pluto. It's about the same size, about the same brightness.
Originally, Triton was probably a Kuiper Belt object just like Pluto, floating around in space, but then it got too close to Neptune and it got captured by Neptune's gravitational field.
Recently, Paul Schenk enhanced the original Voyager data to create this detailed flyover of Triton.
It has odd patches and odd blob-like features, kind of like amoebas crawling around on the surface. Triton has very few impact craters. Its surface is extremely young geologically.
And it actually has geysers spurting material off into space.
Here is a body that is hundreds of degrees below zero. It's so cold, it's forlorn, it's barren. We just didn't expect to see this activity on Triton. It was quite a surprise.
If you just assume that Pluto was going to look exactly like Triton, which is the most similar object we know about, then you might expect to find a very interesting body.
But Triton is not the only dynamic ice world in the outer solar system. 16 years later, the Cassini spacecraft sent back images of Saturn's moon, Enceladus, about 300 miles across.
This is a tiny little moon, and Enceladus is actually a winter wonderland. It's very bright. It reflects almost all the radiation that falls on it, and it has these huge ice volcanoes spewing out from its south pole.
And Enceladus is continuously giving off puffs of water vapor, and so if you start to see puffs of water vapor coming off Pluto as New Horizons gets closer, that would be exceedingly interesting.
But what forces can power volcanoes in the deep freeze of the outer solar system?
Triton and Pluto are both balls of ice with presumably rock in the center, and so one of the sources of energy is radioactive decay inside the rock, which gives off heat, just like the Earth is heated. If you just let Pluto sit there and pump the heat out of the rocks, you generate enough energy to melt a couple of 100 kilometers worth of ice. It's still possible to have an ocean beneath a relatively thick ice shell. The ice shell might be 100 miles thick or so. Over billions of years, the ice shell gets thicker and thicker and thicker as Pluto cools, and as it does so, it squeezes the water underneath, and if you squeeze the water too much, then it may well actually create fractures and the water could jet out to the surface.
When you're going out to the edge of the solar system, you kind of have to expect some surprises, and we're going to see them at Pluto as well.
Just as Triton and Enceladus were mere dots before spacecraft reached them, until now, Pluto has been an astronomer's planet. That's about to change.
We are going to start off as astronomers, and we'll be using astronomical tools to try and sharpen up our images and pull every last little bit of detail out of these fuzzy blobs. We gradually turn from astronomers into geologists as we get closer and it becomes a real world.
Jeff Moore was in the room at JPL as those Triton images came down, but he also enjoys field work and thinks we'll recognize some similar planetary processes at work on Pluto as back on Earth.
So I'm a geologist, and although we don't expect to see oceans on Pluto, there are common processes which operate on this planet, which are likely to operate also on Pluto and its moons.
While the scales are very different, erosion shapes landforms here on Earth and all across the solar system.
There are these little finger-like projections that are formed by the process of erosion, where wind and water have sculpted this landscape by taking advantage of small differences in the strength of the original rock, creating large, huge, fantastic landscapes, such as on Jupiter's moon Callisto, and we can anticipate that we may perhaps also see landscapes like this on Pluto and its moons.
Pluto's 248-year orbit is more eccentric than our solar system's terrestrial and gas giant planets, greatly varying its distance to the Sun. But it's typical of many other objects in the Kuiper Belt and newly discovered planets around other stars. That, plus its highly angled polar tilt, combine to produce strong seasonal effects.
In fact, the seasons of Pluto are amongst the most extreme of any seasons on any world that we know of orbiting the Sun.
And those extremes may be one reason why its surface is also extremely contrasty.
Pluto is perhaps the most intensely bright and dark place that we've seen in the solar system. This dark surface collects more heat. It warms up like asphalt does on a sunny day here on the Earth. And if there were frost that had settled on this dark surface, they're being heated up and driven off, and the transportation of this material could also be creating wind. So you might see small dunes oriented along the periphery of the dark surface, showing this process in action.
For planetary scientists, color can be a clue to the composition of surfaces that can't be sampled directly.
On the Earth, these kinds of colors from red to dark gray are generated entirely by the presence or absence of rust. On Pluto, we see also these same ranges of colors from gray to bright white to yellow to red to black, but there it must be due to a completely different process.
At NASA's Ames Research Center near San Francisco, longtime Pluto researcher Dale Cruikshank and postdoc Chris Matarese conduct experiments to see what processes might create the colors we see on Pluto, starting with gases like methane and nitrogen and the extreme low temperatures we know are found there.
In our cold chamber, we can produce a thin film of ice and then after that expose them to a beam of electrons, which are charged particles, comparable to what comes in to Pluto's surface from space. We find that when we shine ultraviolet light or electrons on simple molecules, before too long the simple molecules are broken apart, and by natural processes they reassemble into more complex chemicals. So far, the colors we make in the lab from irradiating these ices is fairly close to what we see on Pluto. There are tones of yellow, light brown, up through fairly dark red. And if we carry the processing by ultraviolet light to an extreme degree, the material actually turns black. And this is almost the color of pure carbon.
Seeing how radiation transforms simple ices into complex and colorful organic molecules should help interpret the close-up views of Pluto's surface that'll be sent back by New Horizons.
Color translates to the duration of the exposure of these otherwise colorless ices over a year, 10,000 years, 10 million years. That may in turn tell us more about the nature of the exposure of Pluto's surface and even the age of Pluto's surface.
Dale Cruikshank began observing Pluto back in 1976. Now, 39 years later, he's ready for its close-up.
We can say that Pluto is chemically active, chemically dynamic. We don't know yet if it's geologically active and dynamic, but that's what New Horizons is going to tell us. We've been surprised in that way before as we've passed other planetary bodies that we had thought were totally cold, dead, inert worlds, and find that there are geysers, there are ice flows, there are cracks, and all kinds of evidence for geological activity.
I can still remember the first time I saw Pluto in a telescope, and it was just a little dot that you could barely see. It will be amazing that within a period of hours, it will be transformed from this tiny dot that I studied as an astronomer to this huge geologic world that will be able to see volcanoes and faults and ices and mountains and craters. I mean, it'll be truly an amazing experience to see it transformed.
So, from sophisticated lab experiments, from exploring other worlds, and from applying insights from terrestrial processes, what should we expect when we get to Pluto in July 2015?
But the only thing that would surprise me would be if we turned out not to be surprised.
But enjoying the scientific surprises to come means avoiding dangers on the last few million miles to Pluto. That's next. December 6, 2014. In Mission Control, Alice Bowman and her team wait to get confirmation that New Horizons has exited what's called hibernation. For 2/3 of its 3 billion-mile journey, most spacecraft systems have been turned off, saving wear and tear on the science instruments. New Horizons sends a simple signal once a week just to say, "I'm still A-OK." Alice's team has a unique way of showing spacecraft status. When New Horizons is hibernating, their bear mascot is safely asleep. When the spacecraft wakes up, they put on its party hat. If all goes well, this will be the 18th time spacecraft and bear have woken up. But December 2014 is different. VIPs from NASA are on hand. 2 film crews document the action as Alan explains the benefits of hibernation.
It lowers our cost because we don't need to have people babysitting the spacecraft 24/7.
Outside interest in New Horizons is building. If all goes well, New Horizons will stay awake, flying by Pluto in July 2015, and then returning data until October 2016.
Copy that. Thank you, GNCs.
Tonight, data trickles in, and Alice has to wait to be certain New Horizons is fully awake.
We should be getting it momentarily.
It should be any minute now.
It's like watching paint dry. I figure if I stare at the screen hard enough.
And Packet 5 just came in. There we go.
There we go. PI, PM, Mom on Pluto 1. We have a nominal wake-up of the New Horizons spacecraft on its way to Pluto. We're ready for our next leg of the journey.
Was awake.
Our bear. He's going to be here for a while.
This is a watershed day. We have completed the cruise across 3 billion miles of space. The spacecraft is now awake.
Finally, after 9 years, I'm glad to see hibernation behind us and active ops ahead. On to Pluto.
But there are still hundreds of tasks to ensure a safe flyby in July 2015. January 27th, New Horizons has been sending back technical data and all seems fine. But today is the first time Hal Weaver and Andy Cheng will be seeing new science images.
I saw it pop up here. Yeah, let's try that again.
Cheng is lead scientist for the LORRI camera.
LORRI is used for navigation to find the targets and to correct the trajectory so we get to the right place at the right time.
Voltages, currents, temperatures all look normal. No error messages.
This is it. Now let's check out the very first images. And then Sharon, right there, peak pixel 55.
That's right.
Okay. All right, so there they are. Let's look at the whole
For
field.
project scientist Hal Weaver, even the jump in size from 1 to 2 pixels was significant.
This is a real milestone in the New Horizons mission, the very first images of Pluto in the Pluto encounter year. Hadn't turned Lori on, hadn't gotten any images since last summer, last July, but this is it. This is the start of it.
How she blows.
We really don't know what we're going to see. That's what this mission is all about. What is the surface of Pluto really like? How big is it? What are the orbits really? So it's nothing but delightful surprises coming for us.
But some of the surprises may not be quite so welcome. As New Horizons gets still closer to the Pluto system, Lori will be able to identify small moons and possible rings that can't be seen from Earth. John Spencer is leading the UHAZ campaign. UHAZ stands for Unknown Hazards.
We may find new moons or even rings around Pluto. And if we see anything like that, we're going to want to determine whether it poses a threat to the spacecraft, because if it does, if there's debris that we might run into that might damage or kill the spacecraft, then we want to evaluate that hazard and determine whether we should take any evasive action.
To find out just how vulnerable New Horizons might be to even tiny dust particles, the mission sent samples of spacecraft components to the White Sands test range. Technicians at White Sands set up gun tests to assess how vulnerable New Horizons' outer covers and cables might be.
We went to 2 facilities that could shoot things into parts, models of the spacecraft.
While the results might look dangerous, the mission has options to take evasive action.
One of the backup strategies we have if we feel we need to give the spacecraft extra protection is that we orient it so that the high-gain antenna here, which is literally pretty bulletproof and can protect the spacecraft, is going to be facing forward in the ram direction. This is ram in the sense of battering ram. It's a direction in which stuff will be coming at us and ramming into the spacecraft. And if that is facing forward, then any dust particles that hit the spacecraft are most likely to hit that antenna where they won't cause us problems, and only a small part of the spacecraft around the edges is going to be exposed to those particles.
That would protect the guts of the spacecraft, but limit the pointing of the cameras.
The cameras are fixed to the spacecraft, so if the spacecraft has to point in one direction, the cameras can only point in a limited range of directions. This limits the amount of times we can photograph the system as we go past, because we can only photograph objects when they're just in the right angle that we can look at them while protecting the spacecraft with the main antenna.
Another option is to take different trajectories through the Pluto system. That's called the Shabbat play.
Shabbat is the best acronym in the space business. It stands for Safe Haven by Other Trajectory. And it is the word we use to represent our backup plans at Pluto. The second Shabbat takes us much closer to Pluto, into the region where atmospheric drag depletes orbits of any debris, which we think would be the safest Hail Mary pass that we could fly if we have to do something different than the nominal. We are coming into the Pluto system with the ability, if we learn something we don't expect, to be able to make a change and get the goods.
But those decisions can only be made in the last month before closest approach, and there'll be limited time to evaluate the best options. So in February 2015, Spencer's UHAZ team, including ring specialist Mark Showalter and postdoc Simon Porter, are running through a readiness test. Now they're on the clock and being scored for whether they can work through the calculations fast enough to decide on a trajectory correction maneuver that might prevent loss of mission. And that makes this exercise more critical than any that have gone before.
The difference between this and previous operational readiness tests is that this is where we have to demonstrate to the project and NASA that we can do this.
But the only test that really matters comes on July 14th, 2015. That one day will pay off 26 years of dreams and 9 years in flight. For the science team, the year of Pluto began with another meeting to review the latest data on the Pluto system and to hear updates on how the spacecraft was performing. Mission manager Glenn Fountain, who'd been with the project from its start, summarized remaining risks. Red boxes are possibilities that could kill the mission. But now, in 2015, there are more and more green boxes, risks that have been minimized.
Something that we haven't thought of still might happen, but I'm confident that whatever happens, whatever fate throws at us, this team will be able to resolve it, and we'll go on to get wonderful data when we get to Pluto.
We have a fantastically talented team of people who have worked very hard, and we've tested the sequences inside and out. And while there are always unknown unknowns, I'm very confident and really looking forward to the curtain rising.
Along with mind-bending technical details, there also was a sense of history in the making. To document the long years of effort to get this close to Pluto, the mission recreated a team photograph taken in 2004. As Glenn, Alan, and Alice had carefully planned back then, many of the scientists and engineers were still actively engaged in New Horizons and looking forward to July 2015.
We have worked hard to get a coherent team, because if you don't have a good team to operate the spacecraft, to do the planning, you will fail. And so we worked a plan early in the mission to have younger people with the right amount of experience to be on the mission. And it's just like watching your kids grow. It's like all of a sudden, where did the time go? You know, they are older, they're more mature, and they're now the very experienced veterans.
But the hard work of mission planning was by no means over, even this close to Encounter Day. While exploring Pluto in 2015 is exciting in itself, New Horizons was recommended in part as a mission that might continue on, farther out into the Kuiper Belt. That takes identifying potential targets now for a still more distant flyby, should NASA approve an extended mission. This challenging task was assigned to John Spencer, Mark Bowie, and a team of young postdocs. And like everything else about this mission, it wasn't easy. Bowie and John Spencer had been using Earth's largest telescopes in Hawaii and Chile, but even Earth's best couldn't crack this task.
But the basic problem is the Earth's atmosphere is just a mess at these scales. There's a limit, and that's what we've been beating our heads against. Now with time running out, we had to turn to Hubble. And so we sort of, not so jokingly, talk about Hubble to the rescue. Without Hubble, we would not have these objects.
Mark and his young collaborators came up with innovative search techniques using custom software.
What that does is makes the stars smear out and makes the Kuiper Belt objects hold still.
It's been a lot of work, but to do something as exciting as this has been just so much fun. I've been plugging through the data today because it's fresh data, and I just really, really wanted to know what the answer was.
Well, we would have been in big trouble if we didn't find the KBO in time. So there was this pressure, but honestly, we had the best people in the world working on the problem, and we did it.
And we just do the math, write the software, crunch the pixels, and then I create this graphic, and from that point on, it's what I call wetware. It's what you got in your head.
In reality, KBOs are moving against the fixed stars. Mark came up with a way of making them more obvious by flipping that around and making the stars appear to move, and any KBOs stand still.
Right in the middle, there's something that's just holding dead constant. And that's the Kuiper Belt object. You can't argue with that.
It was a high-tech variant of the approach that had been instrumental in exploring the Pluto system right from the start.
But at the core, it's a technique that hasn't really changed since Tombaugh's day. You have two pictures of the sky taken at different times, and you're looking for the stuff that moves. As soon as you see something real, there is absolutely no question about it. As soon as it flashes on the screen in just a millisecond, there it is, it's real, and you know, I've found another Kuiper Belt object.
But finding a KBO is only half the battle. Is it located where New Horizons can reach it with available fuel?
Once you have the orbit, and we know where the spacecraft is and where it's going to be, we can figure out how much fuel the spacecraft is going to need to use to get to these objects.
With more Hubble time, New Horizons got a pleasant surprise.
It looked like we might actually have to burn the engines to miss the object, which was a pretty exciting concept. You know, it's a good thing we looked, because you wouldn't want to run into one of these things.
These cold classicals, they're pretty much as they were 4.5 billion years ago. They're little fossils. That's incredible. We have no idea what they're going to look like.
So with potential targets found at last, it was on to Pluto.
I'm feeling pretty exhilarated at this point. You know, you're at the top of the roller coaster, you're about to go down that dizzying, thrilling ride into the system. Just seeing Pluto there getting bigger and bigger, it gives me goosebumps.
Today, we're only a few months away from the encounter. We're less than an astronomical unit, the distance between the Earth and the Sun, that distance away from this fascinating object. It's the last major body in our solar system that we really need to visit.
To be putting the capstone on the initial reconnaissance of the solar system, it's heartwarming, and it feels like something that makes a career worthwhile.
As spacecraft goes, New Horizons is a very small team, but still, we've been working on this for over a decade, and you add it all up, and it's about 2.5 million work hours to get ourselves to Pluto.
We have waited first the 4 years that we couldn't hardly think about because we were running so fast, and then it is, oh, we wait, and we wait, and now we are ready to begin the encounter. We have had delayed gratification.
The year of Pluto is, you know, simultaneously a beginning and an ending. It's an ending in that we are completing our objective. We're accomplishing the flyby of the Pluto system for the first time. But it's also the beginning of a whole new chapter for science, of really being able to explore these objects as the data comes down over a period of months. You know, in bringing in postdocs and the younger scientists who, some of whom were in high school when we started this project, and now they have their PhDs and they are spectacular experts and very talented at what they do.
I was in preschool when Alan first started talking about a Pluto mission, and finishing high school and starting college when it was built, and in grad school for the cruise.
Having young people come into these programs, gaining the experience, they're going to be the next generation of explorers.
We've never been to a KBO. We've never been anywhere close to a KBO. This is the most unexplored area of the entire solar system, which is another way of saying this is the most unknown area that we as humans can reach with spacecraft.
We can't wait to get to Pluto and to July 14th and see what the surface looks like. We're ready to go, and it's showtime.
We are capable of continuing an adventure that humanity began 100,000 years ago as our ancestors walked out of Africa. And we are continuing that exploration, and this country is in the forefront of doing that.
Well, good afternoon, and welcome to NASA headquarters in our nation's capital. I'm Dwayne Brown from NASA's Office of Communications. Following the July 14th historic Pluto flyby by NASA's New Horizons spacecraft, the research team has begun sharing the unprecedented images and science findings with the world. And today, they have more. Ladies and gentlemen, this mission has clearly been embraced by the entire world of all ages. In fact, the numbers that are coming in with multimedia, social media, the internet, radio, TV, is in the billions. We also want to give a NASA headquarters shout out to the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, for the unforgettable moments at their facility this week. And we have now transitioned here to NASA, where the future media briefings will be here. We'll have brief presentations, and then we'll open it up for questions starting here, our NASA centers, social media, and the phone lines. Social media is absolutely exploding with this mission. Follow the conversation at hashtag Pluto Flyby, Twitter, Facebook, YouTube, and other NASA accounts on that. And if you have questions, send them in at hashtag Ask NASA. And certainly all the information you have been hearing, will hear today, and in the weeks and months will be online at www.nasa.gov/New Horizons. Let me introduce you to today's participants. First up, Jim Green, Director of Planetary Science Division at NASA headquarters. Alan Stern, New Horizons Principal Investigator at the Southwest Research Institute in Boulder, Colorado. Randy Gladstone, New Horizons co-investigator at Southwest Research Institute in San Antonio. Fran Bagenal, New Horizons co-investigator, University of Colorado, Boulder. And Jeffrey Moore, New Horizons co-investigator at NASA's Ames Research Center in Moffett Field, California. With that, turn it over to you, Dr. Green, to kick us off.
Thank you very much, Dwayne. Today we're going to talk about some of the fantastic discoveries about the heart of Pluto. But before we start that, what I'd like to do is really talk a little bit about the heart of the New Horizons mission. First, I want to thank APL and SWRI in particular for all the work that they've done making this mission happen. There's a whole series of contractors, our industry community, that's really made this mission the spectacular success that it is. APL hosted a fabulous historic event this week that many attended personally, but millions attended virtually, which has really been captivating. What a historic week. In particular, the heart of New Horizons that's beating and beating well and beating still was put on and produced by the Department of Energy, one of our major government partners, and that's with its radioisotope power enables us to move further out into the solar system, and it's on a trajectory to leave. Well, currently, if I can have our first graphic. Here we see New Horizons past Pluto. This is through the ISON solar system that you can get access to through the web. And as you can see, it's more than 2 million miles away from Pluto. You know, for 10 years, or nearly 10 years, the New Horizons team, we're always talking about each day we're closer to Pluto. Well, now each day we're further away from Pluto. But here's where it comes in that's important to remember, and that is it's during this time that we're going to be able to obtain the data from the flyby. Right now, we've only received 1 to 2% of that data on the ground. By next week, we'll have perhaps as much as 5 or 6%. And so some of the discoveries that you're going to be hearing about today has only been the tip of the iceberg and the few percent that we were able to get down since the encounter occurred on Tuesday night. And so without further ado, let me turn it over to Dwayne to introduce our next speaker.
And Alan, go for it. All yours.
All right. Hey.
That was
someone who doesn't need an introduction.
Fantastic. Well, we're really happy to be here, and I want to say on behalf of our entire team, we've just had the most fun communicating about exploration and about just how exciting solar system exploration is this week. But I think Pluto's becoming a brand. It sort of sells itself, and we don't really have to work all that hard. I do want to recognize the team members who are here. We have quite a number of members of the New Horizons mission team. If they would stand up to be recognized, if you're working on New Horizons, thank you very much. We also have, and I'd like you to recognize some New Horizons mission educators who are in the audience. If you'd stand up to be recognized. And then finally, Finally, I'd like to recognize one of our science team collaborators who's come over from Europe to help us work with the data a little bit. Some of you may know Dr. Brian May. Brian?
Hear me? Probably not. I'm the guy, I'm one of those people in Europe who's been following your every moves on our laptops and TVs in our offices and in our bedrooms. It's a thrill to be here with you, and what an amazing achievement. You have inspired the world. Thank you.
Thank you. Well, while you enjoy this beautiful eye candy, the Pluto-Charon system is revealed by New Horizons in color. You really see a binary planet. Enjoy that view while I tell you a little bit of news about New Horizons. The spacecraft is doing very well. As Jim said, we're now a little over 2 million miles on the far side of Pluto. Spacecraft's performing according to plan. We exited the 9-day close approach encounter load just yesterday. We're now in the first of our departure science load. So we're looking back at the planet in that special geometry, looking at the night side, and doing various experiments and splitting our time also downlinking data. And we have been downloading a lot of data. So we have some big news, and I expect we'll have more big news next Friday when we've downloaded even more. I'll have to tell you, I'm a little biased, but I think the solar system saved the best for last. So I'm going to show you some things, and if I can have my, I'm going to start off with a little news, and then I'll pass it along to my colleagues. If I can have the next time step, the next graphic, let's see if we can bring that up. There it is. Okay, that's not very many pixels across, but that's Pluto's satellite Nix in its first well-resolved image. Now, let's set our expectations properly. As little as 3 months ago, we didn't have pictures of Pluto this good. And this is actually about twice as many pixels as the best Earth-based views of Pluto. We were able to determine Nix's size, about 25 miles across. We're able to measure its brightness. It's intermediate in brightness between Charon and Pluto. In this view, we believe we're looking roughly down the pole of an elongated object, not as elongated as this pin. It's about twice as narrow in one direction as it is long, and we're kind of looking down the barrel of it right there. We'll have more to say about Nix when we get more imagery on the ground, but a fascinating satellite. And I'll move to the next time step. This is a overlay of some data from the Ralph instrument, from the composition mapping spectrometer, that for the first time identifies the location of a carbon monoxide-rich region on Pluto that had been observed from Earth for quite a long time. But now we can actually overlay it on a map. So that's a New Horizons map product overlaid with contours for the abundance of this carbon monoxide. And you can see that the peak is on the western side of Tombaugh Regio, or the heart. Very nice to be able to do that. Now, you can see it's pretty concentrated spatially. We're not sure we understand that, understand the origin of that. It could be that there's a source region there, and we'll be looking for it hard in high-resolution imagery. Or there could be another explanation, but either way, it definitely catches our eye, because across the rest of this disk, there's no other carbon monoxide concentration, anything like this. We already know that. So it's a very special place on the planet. Randy will shortly show you some pretty profound results concerning the atmosphere. In fact, the first results that we'll share with you about the atmosphere, and Fran will show you the detection of escaping ions from Pluto made by our plasma instruments. And then Jeff's going to talk about new terrains imaged at high resolution. I'm going to give you a little preview of that. So if I can have the next graphic, have a look at the icy, frozen plains of Pluto. Who would have expected this kind of complexity? And by the way, this scene is essentially adjacent, neighboring the mountain ranges that you saw a couple days ago. So we can see that there are stark contrasts on Pluto in terms of the geology. Jeff will show you a lot more of that, but I want to show you something else. I'm going to show you a graphic. It's a flyover made as if your eye was 25 miles over Pluto, and we can go ahead and start that. A flyover of faraway mountains and plains in the Kuiper Belt. If they can go ahead and call that up, I think you'll enjoy seeing it. If we can lower some of the, probably can't lower house lights given the television. Is that graphic available, the animation?
It's being shown.
There you go. We can't see it back here. There it is. Yeah. What you're looking is a scene that's about total width about 250 miles across, 400 kilometers. And these mountains soar as high above their local terrain as many of the mountains in the Rocky Mountains do here in the United States. Pretty impressive. The second flyover is of the plane that I just showed you, which we're informally calling Sputnik Planum. Well, Sputnik was an explorer too. This scene is just as wide, 250 miles across. Gives you a feel for the scale of the features that you were looking at. Really beautiful, beautiful surfaces. And we're going to be seeing a lot more of this. This is 400 meter per pixel imagery. And by next week, we'll have more than twice as much as the 3 frames that we've already been able to share by the end of today. And we'll share that with you as well, covering a lot more terrains. I think with that, I'm going to turn it over to Randy Gladstone to tell you about some early atmospheric results. Randy.
Okay, thanks, Alan. If we could go to the first time step, and I'll show you what the atmospheres team is looking at. We have had to wait until we got past Pluto, and we're looking back towards the sun to get our best data set. This shows you on the left an animation of what it's like when the Pluto goes in front of the sun as seen from the spacecraft. And the curves on the right show you 2 plausible atmospheric models for Pluto's atmosphere. And here we show you the data that we got coming down. And it's just count rate data. Each one of those points is 10 seconds, but we get, for every point on there, we'll get a whole spectrum. And then on the way out, if we flip it, you see the green line goes back exactly the same spot. So the atmosphere is very symmetric on opposite sides of the planet. And it seems to be more consistent with the red line, which is a more sluggish atmosphere or stagnant atmosphere. So we've already eliminated, just from this little bit of data that we got, a glimpse of the data tells us, or eliminates a couple of models that were contenders up till now. So the next slide shows you, that was zoomed in at just the surface of Pluto, but we see the atmosphere way far out. So this is how our count rate went from the beginning on the left to the end on the right in the red and white curves. And Pluto's shown there in the middle. So we see the atmosphere all the way to the ground. From Earth, that inner circle around close to Pluto is the limit, the highest the stellar occultations from Earth can see. And they can't see to the ground. They can only see to 30 miles above the surface or so, out to 170 miles. We see from the ground out to 1,000 miles above the surface. So you can see this isn't a straight, simple curve. It drops slowly, and then it picks up, and then it has another bend where it picks up again. At the highest altitudes, that's nitrogen, molecular nitrogen, the main component of Pluto's atmosphere, starts to absorb the sunlight. And then lower down, methane kicks in, and then even lower down where it gets steepest, that's heavier hydrocarbons near the surface that are absorbing the sunlight. So, like I said, each point on this graph will be a whole spectrum of colors in the ultraviolet light that we're getting this signal from. And we're really looking forward to getting that data in a month or 2. So, but it's very tantalizing right now, and it already is, we're able to do science with it. But that nitrogen atmosphere, because Pluto's so small, it escapes directly into space, and Fran is going to tell you what it does out there.
So we've had 9.5 years of this flight out to Pluto to think about what are we going to see with the plasma instruments. And we are seeing all sorts of things. We haven't got all the data down yet, of course, like all the other instruments, and we're really looking forward to getting it down. But in the meantime, let me tell you a little bit about what we think is happening. So Randy has already discussed that we know the atmosphere is nitrogen, and we suspect it's escaping because of the weaker gravity on Pluto. It's about the gravity is a lot weaker than Earth and than Mars, and so we know that it's going away. And what we think is happening is that the solar wind that comes from the sun, the protons and electrons, charged particles that are streaming out at supersonic speeds will eventually crash into, they'll interact with this escaping atmosphere, and that this will then produce, we suspect, a shock upstream. Maybe it's not quite so stark. There's some, we know that there's an upstream amount of nitrogen ions. We've already observed that with New Horizons, with the PEPSI instrument, well upstream. And that was energized by the solar wind and carried away by the solar wind. But the real question is, what happens as it interacts with the denser escaping atmosphere that Randy was talking about? And so what happens is, and this graphic that you're looking at here gives you a sense of what we think's happened, is that as it escapes, the atmosphere is ionized, it's picked up by the solar wind, and the size of this interaction region actually fills out beyond the scale of the satellite. So it's a large volume. Now, we have actually flown through this with the instruments, and the next slide will show you what we think is happening, is that SWAP now has actually detected the ionized atmosphere. These are nitrogen molecules that are being ionized by photons, UV photons from the sun, and then once they're ionized, they get entrained in the solar wind and carried away. And so what we see behind Pluto is a tail, an ion tail of this ionized escaping atmosphere that's being pulled away and carried away in the solar wind. Now, when we get the rest of our data back in August or so, we really will be able to quantify, when we add the data that Randy and the atmospheric team put that together with the SWAP and PEPSI observations, we'll be able to quantify the amount of that escaping atmosphere. What we think it is, based on models and a pretty good guess, is about 500 tons per hour of material that is escaping. And this is, for comparison, we know that the escaping atmosphere for Mars, which is being studied by NASA's MAVEN mission, is about 1 ton per hour. So this is substantially more because of the weaker gravity on Pluto. Now, what is the consequence of that? Well, if you add that up roughly over the age of the solar system, or the age of Pluto, this is going to be equivalent to something on the order of 1 to 9,000 feet. So that's a substantial mountain of ice, nitrogen ice, that's been removed through this evaporation and then escape into the atmosphere. And Alan Stern has worked with Simon Porter and Amanda Zangarian predicting what this will do to the geology. And they have a prediction paper. But Jeff and the geologists are going to look at the geology and tell us what actually happens.
Indeed, we will. Well, I'm still having to remind myself to take deep breaths. I mean, the landscape is just astoundingly amazing. In fact, let's go back to this picture that we talked about a few days ago. It was still a global view. And remind ourselves that the global view shows some surfaces on Pluto are peppered with impact craters and are therefore relatively ancient, perhaps several billion years old. Whereas other regions, such as the interior of the heart, which we've now named Tomball Regio, show no craters at all, and are thus obviously younger, and indicate that Pluto's experienced a long, and thus all of this suggests that Pluto's experienced a long and complex geological history. And so this means that there are active landform creating processes operating into the geological current times. Now, some of the craters appear partially destroyed, perhaps by erosion. And there are also hints of parts of Pluto's crust that have been fractured, and thus that indicates there's probably been some forms of tectonics. Now that we've seen mountains, I think there's pretty obviously mountain-building forces operating on Pluto. And also, some of the higher resolution images, show that there are craters which may have been partially eroded away. So erosion processes also seem to be operating on the surface of Pluto. And then, may I have the next time step, please? The next slide, please. So let's zoom into our 3-image mosaic of the 400 meter per pixel imaging that we've taken. And here you can see there's the provinces of the 2-mile-high mountains, which we're now calling Norgay Montes, which are located in the lower left. There is extensive large-scale pitting, you can see in the lower right. And then there is this extremely young plains, which makes up the northern half of the upper half of the image. And by the way, this image is oriented so north is up. Being a geologist, I kind of like that. Makes life easy. And this is just a taste of what I'm sure is in the unsent data. So may I have the next slide, please? And so you see there's the names that we've assigned to them. As Alan mentioned before, we decided to name Sputnik Planum after the first artificial satellite launched into space, and thus beginning the space age. And Norgay-Montes, of course, is after the Nepalese Sherpa who went up the Mount Everest with Edmund Hillary, and is the first Nepalese to have a name on any planet in the solar system. Okay, let's have the next time step, please. Okay, let's look at this little region here in the middle of Sputnik Planum. May I have the next time step, please? Okay, when I saw this image the first time, I decided I was going to call it not easy to explain terrain. So this is the frozen plains of Pluto. You know, so when you look at this plains, you can clearly see that we've discovered a vast craterless plains that has some strange story to tell. For convenience, as I said, you know, we've tried to think about in various types of geological metaphors, which I'll get to in a moment. But judging from the absence of impact craters, it's clear that Sputnik Planum, you know, couldn't possibly be more than, you know, let's pick a round number, 100 million years old, and possibly still being shaped to this day by geological processes. So this could be, you know, only a week old for all we know. In this image, you can see things as small as about a half a mile across. And then let's talk about some of the things we see in this scene. So let's go to the next slide, please. The surface is broken up into polygonally shaped segments, which you see are listed on this slide as irregularly shaped segments that are roughly 12 to 20 miles across. They're bordered, as you can see, by what appear to be shallow troughs. Some of these troughs have some darker material that seems to be in them. I don't know if that's material that's collected there or erupted there. I don't know, but some of the troughs do have what appears to be just dark stuff. Much more enigmatic are these clusters of hills, which I think you can see pointed out in the upper right of the frame. They appear to be elongated clumps of mounds, and they trace out the shapes of the troughs that encircle the polygons. About the only thing we can say about the hills, except for their smoothness, their mound-likeness, is that the hills are higher than the surrounding terrain. We don't have a value for that yet, but this is part of a bigger stereo mosaic sequence we took. So when we get all the data down, we can tell you exactly how high they are and exactly how they're shaped, which will go a long way to help us interpret what, in fact, created these hills. We have, and thinking of the hills, we suspect that either the hills may have been pushed up from underneath along the cracks, but alternatively, a completely different explanation is that they are erosion-resistant knobs that are standing out as the surface is being massively eroded and lowered. So we don't know which of those two explanations is correct, but you can see that we can go either way. They can either be popping up or emerging from a erosion lowering process. It's lowering the entire plains. In the terrain in the lower right, I think you can see there are several of the polygons appear to be etched by fields of small pits. Now, while this identification is a little tentative because there are still compression artifacts in this first batch of data, which has been sent down to the ground with velocity compression, we will very soon receive these same images without any compression. And I think the issue of whether that is indeed vast scenes of pits will be verified probably pretty straightforward way. Similar features to these vast pitted surfaces can be seen, for instance, on the surfaces of glaciers here on the Earth. And on terrestrial glaciers, this is caused by erosion from wind and sun. But on Pluto, the erosion mechanism would have to be a process called sublimation, which is when the ice turns directly from solid to gas in the way frozen carbon dioxide or dry ice does on the Earth. So what do these features tell us about Sputnik Planum? One possibility out of many is that the polygons are signs of convection occurring within a surface layer of carbon monoxide, methane, and nitrogen ice, driven by the modest heat from the interior of Pluto itself, creating kind of the same sorts of patterns you see when you look at the surface of a boiling pot of oatmeal or like the blobs in a lava lamp. But alternatively, these polygons could be analogous to mud cracks, and they could be created by the contraction of the surface materials. But we have various ways to test those ideas, which we'll be using and reporting out in forthcoming conferences and scientific papers. And as I said before, we will learn more about these enigmatic features and terrains and much higher resolution and stereo coverage, which is still up on the spacecraft and going to come down in the next few months. And in fact, I think 20 years from now, people are going to look at the coverage we have of Sputnik Planum in particular and think we planned the whole encounter around looking at Sputnik Planum. But that's just a pure coincidence. It just worked out that way that the fates of space exploration, favor us to put some of those interesting places, directly in the sites of our highest resolution, highest quality data. So this is going to be really fun. Okay, so to be a little more speculative, we also saw one other thing. So may I have the next slide, please? So let's zoom into this area that's just northwest of the one we just looked at. There you go. Okay, so these dark smudges appear to be aligned and running from upper left to lower right and may have been produced by winds blowing across Pluto's icy surface. May I have the next slide, please? And so on Mars and Earth, similar features are what scientists call wind streaks and are produced when prevailing winds cause erosion or deposition, we're not sure which of those, material behind topographic obstacles. And don't ask me what the topographic obstacles are because we can't quite tell yet, but we will be able to tell you when we get the rest of our data down. But alternatively, and this is even more speculative, they may be plume deposits associated with glaciers, like those seen on Neptune's icy satellite Triton. The plumes themselves, if they exist on Pluto, have not been spotted yet. So this is not an announcement we've spotted plumes or geysers or anything like that on Pluto. But of course, we will be looking for them in images yet to be received from the spacecraft. So, let me conclude by saying these are the early days of the post-encounter analysis. And as extraordinary and provocative as these images are, we are in the most preliminary stages of our investigations. And we're still entertaining, as you can tell, the widest range of hypotheses. We are acutely aware that jumping to conclusions comes at great peril. So with that caveat, I am going to pass it back to Dwayne.
Thank you all. Let's give this team a round of applause. Much, much more to come. Okay, now we transition into the Q&A. We're going to start here at NASA headquarters with the media and the audience. Then we're going to see if we have any questions from our NASA centers, phone bridge, and of course, social media. So if you can wait for the mic, raise your hand. Do we have any? If we have, and give your name and affiliation, please.
Stephen Young with Astronomy Now magazine. For Alan, we heard about how this is just the tip of the iceberg, and also in these images you can see they're compressed. Can you quantify how much data you've got on the ground right now versus how much is on the spacecraft waiting to come down? And what's the difference going to be in those images when we see the uncompressed versions?
Yeah, I'll be happy to. So we have about, in very round numbers, about 50 gigabits of data that was made beginning about 10 days before closest approach. And by the way, that 50 gigabits is the full amount that we will store through the end of this month as we look back on the system. So that includes data we haven't quite yet taken. All that will ultimately come to the ground with lossless compression, about 2-to-1 compression that doesn't introduce any source of noise. But our lossy compression can accelerate our ability to get data to the ground with the expense of some noise. Some scenes will compress 10-to-1 or even better. So it's a very efficient process at the beginning of the downlink to send home what we call the browse data set. The concerted effort to get everything to the ground that can be compressed will begin in September. and that will take about 10 weeks, maybe 12 weeks, depending upon DSN schedules and other factors. We currently have on the ground less than one of those 50 gigabits, probably around 1 gigabit. I didn't check this morning. We can get you a more accurate number if it's helpful.
Eric.
Yeah, Eric Hand with Science Magazine. My question's for Randy. You mentioned that you think you've ruled out this turbulent model for the atmosphere and that you think it's maybe more sluggish or stagnant. What are the implications of that for transport of materials around the planet via frost? And does it have any effects on maybe what you're starting to see on the surface with these wind streaks? Is this an atmosphere that blows around all the time, or maybe not so much?
Yeah, good question. We still don't have a good measure of the lowest atmosphere, where it's very complicated. The atmosphere, we think of all the atmosphere on Pluto is sort of compressed into a very thin layer near the surface, where the winds can be up to a few meters per second easily, and those numbers are good enough to launch or loft particles off the surface, micron sizes. So it's not inconsistent at all, even with the sluggish atmosphere, to be able to move stuff around still. So we think it's fine, or consistent so far.
Frank?
Frank Mooring with Aviation Week. At this point, have you learned anything that will help you understand what happens to the surface of Pluto as it goes through its long orbit?
Good point.
Anybody else can chip in. So we've understood the physics of volatile transport coupled with atmospheric escape very well for a long time, but we haven't had the boundary conditions to be able to really run those models in a way that we'd like to, because we don't know, for example, we haven't known until now the details of where the bright areas are, where the darker ones are, and that can relate to the way that areas heat up, particularly those places that might be devoid of volatiles and would have higher swings. So in the coming months, we're going to see composition maps, albedo maps, topography maps, and some thermal maps come to the ground, all of which will make tremendous input to be able to inform us how to run those models for the real Pluto. And we're really going to be living in a very data-rich environment, because New Horizons payload was selected to be able to make comprehensive answers about those kind of first-order questions. Because Pluto's orbit is elliptical and the planet's pole vector is tilted over, its obliquity is very high, even higher than Uranus's. It's a pretty complex situation. We know how to model it, and once we get this data on the ground, I think we're going to get some spectacular results. It'll show us not just what happens, Frank, around a 248-year orbit, which itself is pretty interesting, but over much longer timescales. I, for example, am very interested in how the volatiles transport over long times around the planet, and whether sufficient material moves around the planet to actually, or to potentially, bury structures or be removed from structures so that we see them at different times in Pluto's seasonal cycles. The climate cycles have very long periods in some cases. Everybody's aware of the 248-year orbital cycle, but the pole vector actually circulates over a 4 million year cycle, which averages over many, many orbits. So running these models is going to be fascinating, and we're going to have the data on the ground to do it. I think we'll really hammer the nail on the head.
Okay, as we're going to come back, I'm going to go to the phone lines. And for the media, like we've had at all of our briefings, there are lots of media from all over the world. They're going to want to try to ask questions. I want to try to get to as many of you as possible, so please limit your questions to one. So we're going to go to phone lines, we're going to go to social media, and then we'll come back here. So on the phone line, up first from NBC News, Alan Boyle.
Oh, thank you. This might be for Jeff or for Alan. Just looking at that hillocky terrain and the potential for plumes, can you say anything further about whether this is Triton-like terrain? What sorts of similarities do you see to what folks have seen on Triton, and how do you hope to resolve the issue about those plumes or wind streaks?
Well, first of all, as I said before, we are not making an announcement that we've seen plumes in any way. As far as trying to compare it with Triton, well, the sad story for Triton is it didn't have a New Horizons encounter. The data set we have for Triton is about twice as, well, let me put it this way. The very best images we ever took of Triton under the best of circumstances are only just as good as the pictures we've shown you so far. And almost all of Triton was imaged at much worse resolution than the images that we've shown you, and our images, in contrast, these are just kind of the middle resolution pictures for us compared to the really good stuff we haven't even seen yet. So part of the problem, it's hard to compare Pluto with Triton in some sense because we need to see Triton better. Having said all that, not only did people see active plumes, did the scientists in 1989 see active plumes on Triton. Triton appeared to be covered with a number of just what looks dark aligned markings, which were interpreted as wind streaks. And so to the extent that we can compare our good data with Triton data, and the best Triton data was not actually over their wind streak terrain, we think they are comparable. I'm sorry that was a long explanation, but that's kind of where we are.
Jeff, it's probably worthwhile for you to speak to the comparative differences to do with our detection of mountain ranges right off the bat and the polygonal terrains.
Well, right. I mean, for one thing, as people have, for many years, since the 1970s at least, wondered whether these very evolved young terrains you see on the giant icy moons of the gas giants were made that way because of a process called tidal heating, where the moons interact with themselves and with the body that they're orbiting around to basically heat up their interiors through friction. And so when people see like Io's volcanoes erupting, Io's a volcanic moon of Jupiter, they are attributed to this process called tidal torque heating. But the question was, could icy worlds, minding their own business, not orbiting some giant planet, also be geologically active? And the answer is obviously yes. Pluto is every bit as geologically active as any place we've seen any place else in the solar system. And this really does answer sort of a fundamental question about, are ice worlds able to do their thing in their own right, and or are they dependent upon the help of the big planets they orbit around?
Next up, Pete Spots, Christian Science Monitor. Pete?
Thank you very much. And I think this is for Dr. Moore. One of the detailed question when you were talking about the height of these hills inside these trenches as being above the surrounding terrain, is that, just to be clear, is that the terrain trenches or the actual interiors of the polygons? And do you have any sort of depth estimates for those troughs and any sort of ballpark estimates for the heights of the hills?
Okay, well, the height of the hills appear, and we don't have any quantitative data to say much more than this, appear to be a little higher than the surface represented by the polygons. We don't have any direct measurements of shadows and so on. As I've said before, we will be receiving data that's 6 or 7 times higher resolution and in stereo. So there's hardly even any point in speculating too much about the height of the hills, and we can give you the answer explicitly very soon in the next few months.
Next up, Ken Kramer, University Today. Ken?
Congratulations, great results. I think my question also is about these polygons. I wonder, Phoenix landed on polygons a few years back. I wonder, is that a reasonable comparison at all? Is there any relationship to them at all, or are they totally different? Thanks.
Well, you are right that when you look at large polygons elsewhere in the solar system, the surface that is most reminiscent of the surface we are looking at is the high altitudes, the high latitudes of the northern hemisphere of Mars. And indeed, the Phoenix lander did land on such polygonal terrain near the Arctic of Mars. Having said that, as I said earlier, that we were really entertaining 2 alternate explanations, and I think right this second we may weakly favor the science team, the geology team may weakly favor the idea that some form of internal convection may be responsible. But as I said, we're still very, very open to the idea that these could be due to contraction, and it's contraction, thermal contraction, that forms the polygons, is essentially responsible for the polygons on Mars, that in combination with sublimation. So they could be more, the process could be more analogous to the processes operating on Mars. It's just really too early to say.
1 second. We're still on the phone line. We're going to do 3 more calls from the phone. We're going to go to social media, and then we're going to come back here for the media and the audience. So next up, Dave Mosier. Hope I got the last name right, from Business Insider. Dave?
Yeah, thank you. Congratulations on the mission. This is for Jim, maybe for Alan. You mentioned the beating heart of New Horizons. There's only so much of that key material left, plutonium-238. I'm curious, what is the status of efforts to make plutonium-238, and how is the current supply crunch limiting future missions NASA is dreaming of?
So currently we have our plutonium is being, of course, managed by the Department of Energy. We do have a fair amount of it. It's approximately 17 or so kilograms of plutonium that is available to us that could be used right away. We have additional plutonium. Doesn't have quite the energy density we need to actually use in these missions, but we've also been given the approval by Congress and support by the administration to be able to start generating plutonium-238, and that's really good news. The Department of Energy has created a process that has, and they've verified it, to take neptunium, irradiate it with neutrons in some of their reactors, and the reaction ends up providing one of the byproducts, plutonium-238, and then that's can be extracted and then stored. So right now, we feel really good that we're in the position to be good stewards of the planetary program for many decades to come. We have adequate reserves of plutonium on the ground, and indeed we'll be making it starting late this decade, early next, on a regular basis.
Kelly Beatty, Sky and Telescope.
Thanks very much, Dwayne. I'm afraid I'm going to jump ahead a little bit in the playbook. For either Alan or Randy, do you see anything in the ALICE or REX data, occultation data sets to suggest that Charon has an atmosphere?
Well, I'll speak to that. We don't have those data on the ground yet. They'll be coming down, I believe. Is that right, Randy, in the next 3 to 5 days? Yeah, Sunday. So we'll get back to you on that.
Soon.
Okay, last question before we go to social media from Mike Wall, space.com.
Thanks, guys. Yeah, this is just a quick one about how, like sort of old all these terrains are. Do we know enough about like impact rates, cratering rates out there in the Kuiper Belt to kind of make some guesses, even on the terrain where there are craters, or are cratering rates out there lower than they are in sort of like closer to the sun, and like is it a totally different ballgame out there?
Well, the way we estimate that is several ways. First of all, we have seen cratered surfaces on the moons of Uranus and Neptune. We can obviously study the larger components of the Kuiper Belt down to a few tens of kilometers across with Hubble and other telescopes. And so by looking at the cratering records on the moons of Uranus, Neptune, even Saturn, and looking at the numbers and objects and distribution of objects in the Kuiper Belt, there have been several studies which have derived an approximation of what the crater flux rate is. So it's far from a precise number, and we can often tell you if a surface is extremely old or extremely young. It's actually harder to tell you if it's an intermediately aged surface. Then you typically have factor of 4 uncertainties in those. But we think we understand the cratering rates well enough to say that if you see a surface which has no craters, it's difficult to understand how it could be much older than around 100 million years.
Okay, as I said earlier, the world has embraced this mission with billions, and social media is certainly a big part of that, and NASA is always looking to reach out to new audiences. So we're going to see what the world is talking about on social media with Jason Townsend. What's out there in the world?
Sure. Our first question here comes from Twitter user Brianna, who asks, how do we know Pluto's atmosphere is escaping? How is that measurement made?
We have not yet actually measured the escape. Okay, we hope to. Currently, it's based on expectations, understanding the gravity of Pluto, that it's relatively weak, and that we expect it to be escaping. Furthermore, we know that there's a little bit of methane, and maybe Randy can tell you a bit more about that, but we know there's methane in the atmosphere, and we all know from Earth that methane is a greenhouse gas that absorbs sunlight, and so that heats the atmosphere, and it's the energy deposition of sunlight into the atmosphere that gives it that energy to escape the gravity. So we're pretty sure that that's happening. We haven't got a direct measurement, but we will, by August, have measurements from both SWAP and Pepsi that will tell us, quantify the amount of escaping atmosphere, which will compare with the atmospheric observations coming from the ALICE and REX teams.
Next question comes from Twitter user Jason, who asks, what sort of material could be responsible for Pluto's dark stains? Organics?
Jeff, do you want to speculate?
Sure. Why not?
I don't.
The least crazy idea, which I think we're still working on, I know that this will hopefully be determined with the spectrometer, with the LISA instrument, is that those dark stains, well, the composition of the dark stains are probably just higher hydrocarbons made by the irradiation of methane. The methane basically can be either irradiated on a surface ice, or it can be irradiated more likely and more commonly as particles high up in the atmosphere, and they simply very slowly rain down to the surface. And for instance, the streaks that they in fact turn out to be wind streaks are probably just these very fine particles that sort of slowly fall out of the atmosphere and collect on the ground, and the wind sweeps them along, and they get caught behind wind traps, behind obstacles, and they're downwind of the prevailing winds.
Let's take one more, and then we'll come back here, Jason.
All right, lots of questions about elevation here. This one comes from George, who says, will the data collected from New Horizons be sufficient to create Pluto and Charon elevation maps?
Absolutely. Absolutely so, for both encounter hemispheres. So for the surface you can see pretty much in the picture on the screen, it's still up on the screen now, we will have, although they will always be at the same resolution, topographic maps for the near encounter hemispheres of both worlds.
Okay, and I want to thank our social media audience, and we're going to answer those questions, get them in at #AskNASA. We have scientists, and we'll get to those answers as quickly as possible, but you can follow the conversation, and those answers will probably be on that conversation. There's a lot of conversation at #PlutoFlyby. So let's come back here. Let me see your hands high here. Let's go here, and then we'll work our way this way. Name and affiliation, sir.
Thanks. Stephen Clark with Spaceflight Now. I know you're not prepared to make an announcement about geysers or plumes. Do you need a direct detection of that, or is there some indirect way you can find some evidence on the surface or in your thermal maps to say you found them?
There might be some indirect means, but you know, I'm an old-fashioned geologist. I wasn't quite born in Missouri. I was born in a state near it. I want to see, you know, unambiguous evidence that something's, you know, erupting up into the atmosphere, and we see it. Don't worry, we'll come and tell you about it.
Lochtawala with the Planetary Society. Alan, for a long time you've been a proponent of and been supported by the amateur image processing community, and you started releasing the raw images. The raw image release was halted this morning. I'm wondering if that is a plan to continue, or if you are going to keep the data in order for the scientists to interpret it before you show it to the public.
Yeah, we intend to continue to release all the LORRI images. However, as we're winding down from the peak of activity after the intensive flyby activities, we're going to move to weekly releases all in one set. That's a manpower thing, and it's also helping us vet the images when we don't have the entire science team assembled. The data is really going to start to flow in the fall. And before that, you know, after the next week or so, one of the things we want to make sure the amateur community knows is that we're going to turn to getting the plasma data and other what's so-called low-speed data sets to the ground. So there'll be a long gap. It's not because we're stopping the sharing. It's because we're not sending imagery to the ground in the month of August and early parts of September. Then we'll start again, and as I said, we'll be on a weekly basis, and you'll be able to count on it like a clock.
So we're going to take a few more questions, then we're going to close out. Leo?
Thanks, Dwayne. Leo Enright with Irish Television. We journalists absolutely love flybys, mainly because it's science at the speed of journalism. And who could possibly not like that? But if you'll forgive me, I didn't want this week to fly by without remarking that this is the first planetary flyby in American history where the imaging specialist Yuri van der Woody has not been intimately involved in distributing the imagery. Yuri was the sixth person at the front table at every flyby. We completely relied upon him to provide us with imagery during those days. Yuri, I don't know if it was something about us journalists, but NASA chose an Air Force pilot, fighter pilot from the Dutch Air Force to deal with us. But he was our link with the imaging teams for my entire professional career. And I didn't want this week to pass without mentioning Yuri. He was a great public servant. He was a terrific guy. And I suppose, as we in Ireland might say, he was a mensch.
Well, he was a really great guy. Even when I was a young student, you could call him, he'd pick up the phone, you could say, "Hi, I'm so-and-so from Pauls Valley, Oklahoma," and he would mail you pictures of the latest encounter. It was fantastic.
Yeah, and for our television audience, Yuri, I knew him, but we also had some unfortunate folks that passed during this time. That the NASA family, ladies and gentlemen, we work very hard, but we care for each other very hard. And we've lost some people, Yuri and others at the Jet Propulsion Lab. So our thoughts and prayers go out. But the NASA family cares very hard when we lose folks. Okay, Eric, and then we'll take one more, and then we'll close out.
Eric Hand with Science again. Maybe we can bring up that image of the carbon monoxide-rich terrain in the middle of the heart. I'm wondering if you can tell us how thick it is. Is this more than just the veneer that you suspect everywhere else? Is it pure? Are there other ices mixed in? And then how did it get there? Is this something that was deposited from above, or could this be something welling up from within? And even if you can't say right now, how would you approach distinguishing between those two things?
Gosh. Go ahead.
All right. I'm going to say a couple words about that, and we specifically brought along our composition team lead, Will Grundy, who's down in the audience, who has a microphone, because we thought we might get a question about that, and his team led the work. We know that what we're looking at is at least thick enough to make that absorption. It's at least the veneer, but it could be quite a deep layer. Will?
Yeah, you said it exactly right. You only need a centimeter or something to produce an absorption of that depth. So we know that there's a lid that includes a lot of carbon monoxide, but how that interacts is potentially quite subtle. It is soluble in nitrogen ice, which is also widespread around the surface, and methane is also partially soluble in that mixture. And so how they combine, we really don't know yet, and we're going to have to do some detailed modeling. I like the scenario of it upwelling from below, but I don't think we're anywhere near proving that that's what's happening.
Last question.
The Planetary Society, it's for Randy. I'm just wondering if you can tell me if you see any signs of atmospheric structure in your occultation yet.
Yeah, those kinks that you saw in the occultation profile tell us where one atmospheric species is absorbed out and the other one takes up. So that's not really structure, but just from the shape of those profiles, we know how extended the atmosphere is. It actually might be a little cooler than we thought, but we'll get that later.
Okay, well, ladies and gentlemen, folks watching from all over the world, the Pluto story is just beginning. You can follow the conversation on all the NASA social media accounts, and of course, go to www.nasa.gov/New Horizons. I want to thank folks for joining us and witnessing history, space exploration. We have another press conference coming up next Friday on the 24th time, TBD. Thanks for joining us. Science never sleeps.
I guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit.
They've got the flag up now, and you can see the stars and stripes on the lunar.
Flag up now, you can see the stars and stripes.
Are you getting a TV picture now, Houston? Neil, yes, we are getting a TV picture. You're in our field of view now. That's one small step for man, one giant leap